We start with the problem of two-dimensional Euclidean distance, and we're going to be using the same example that we used previously, where we basically have 3 points, and they're going to be defined in a 3x2 matrix P. Each row of the matrix represents the x and y coordinates of one of the 3 points. And then, like we did before, we're going to go ahead and create a function handle. And here I'm just going to F9 to evaluate. So I have this function handle. Here I've called it D2H. The 2 is because we'll be talking probably in a later class about metric distances, and they can be described in terms of a parameter, and the value for Euclidean distance of the parameter is equal to 2. A rectilinear distance, for example, has a parameter of 1. So that's the reason for the 2 in the description of this handle. Another thing to notice is that for the x value, before I made note of the possibility of the value being input as a column vector or a row vector, and one way of avoiding that is to put in parentheses a colon, take the transpose, that'll force it to be a row vector. Here I'm not going to include that, and the reason is that within the script I'm going to assume that if I input x in the manner of a row vector, it refers to a two-dimensional row vector if I have 2 values in x, whereas if I input x as a column vector, a 2x1 column vector, then what I'm actually referring to is 2 one-dimensional points. So in this case, I can, in addition to being able to solve two-dimensional problems, I can also solve one-dimensional problems. So I get a little bit more generality. So the row versus column nature of x is actually important for this problem. Again, not for today's description, but as we go forward. So that's the explanation of why I'm not going to do that sort of error checking feature, because I actually want to use the column versus row nature of x as important information to indicate whether I'm dealing with 2 or one-dimensional or more than two-dimensional points. Again, that'll be discussed in more detail in the next video and the next class. And then, like we have done previously, at this point, if you look at the problem itself, what we're trying to do is determine what point within the region between the 3 points is the minimum sum of Euclidean distances. So again, like we've done before, we can go ahead and define a function handle that gives us the total distance. Notice that this function handle is using another previously defined function handle. So we're basically nesting one inside of each other. And then to run the fminsearch procedure, we need to pick a starting point. And one, I think, reasonable starting point, if you want to have a way of sort of mechanically, for any sets of points, being able to define a point, then you can use the mean, which is just the average, in this case, x and y coordinates. So for this one, I'm just going to get rid of the semicolon so I can actually see. In this case, x value of 4 and y value of 2.33 corresponds to the mean value. The advantage of that, as opposed to putting 0, 0 or some other point, is that the sets of points in P could be quite far away from 0, 0. So by taking the mean, I ensure that I have a starting point that's somewhat in the middle of all the points that I'll be optimizing. So that's a way of kind of automatically being able to create a reasonable starting point. And then at this point, what I'm going to be doing is actually implementing via fminsearch the mathematical term called argmin. And what we're doing is we're minimizing, by changing the variable x, the function total distance. And then instead of getting back the minimum total distance, for most problems, we're actually more interested in what is the value x corresponding to that minimum value. And that's the reason for this argument. So we don't want the total distance, we want the value of x that minimizes that total distance. And here I'm labeling it as x star. In MATLAB, you can't label a variable as x star, so we're going to keep it as x. But when I do that, I'm going to F9, and I run it, and I get the solution 4 and then 2.73, which is actually pretty close to the mean value. And then if I want to get what is the corresponding total distance value of that optimal x star value, then I can just call the function handle with the return value from fminsearch. And there the total distance value is 9.1962. I can do it all in one step because fminsearch, and this is true for most of MATLAB's functions that do any type of optimization, usually the first argument returned is the x value, and then the second argument returned is the function value corresponding to that x value. So again, that's exactly what we want in this case, and we get both of those values returned from the fmin procedure. The fmin procedure, as talked about in class, is actually used to implement the Nelder-Mead simplex method, which is a direct method of optimization. And that method is more robust than a gradient-based technique. The disadvantage is it's more computationally expensive, especially if you're working in very high dimensional optimization problems. But in this case, we're dealing just with a two-dimensional optimization problem. So using the Nelder-Mead computationally is not an issue. And now with computers being as fast as they are, it's even less of a reason to need to use any type of gradient-based procedures, which are more computationally efficient, but don't work for as large a class of problems. For this particular problem, any type of optimization technique would work because this is an example of a convex optimization problem. And what that means is for this problem, we can really pick any type of starting point, 0, 0, minus 1,000, minus 1,000, whatever the case, it's just one large surface, and we'll ultimately get to the bottom of the surface corresponding to the optimal point. So this is really the simplest type of nonlinear optimization. You'll see even later in this script a more complicated optimization problem where that's not the case. And then to be able to see what's actually happening, what I'm going to do here is do a plot of the function that we're optimizing in terms of the 3 points. And to be able to display those 3 points, I'm going to use the plot command, which is the default plotting command within MATLAB itself. We'll be using a plotting command that's developed as part of the MATLAB toolbox that allows us to do projective plotting, and that's called pplot. But this is the basic one that's part of any MATLAB procedure, nothing to do with MATLOG or logistics engineering. And the format for this plot command, first argument are the x coordinates. So I'm taking all of the column of the first column, and here I'm taking all of the column indicated by the colon of the second column of the P matrix. So these are all the x's, and these are all the y's as the second argument. And then as the third argument, I'm using an indication of how I want to actually display the marker points corresponding to these points. And MATLAB uses a syntax for indicating the type of format and color and shape of these markers that's a little bit complicated or non-intuitive. So what I find myself doing quite often is here, if I go to the command line and if I just type help on plot, I get all this information. And what I'm really interested in is this information right here. And it's telling you for that little string of characters what it actually corresponds to. So these are all the different characters corresponding to different possible colors. And if I want to plot it as a black color, then I use K. And the reason B isn't used is B is used for blue. So black is indicated by K. And then the second thing I'm using here is S. S, looking in this list here for the second character, S corresponds to a square. Other options are to point, circle, X mark, plus mark, and so on. So these are all the different options for the shape of the marker. These are all the options for the color of the marker. And then this third option here is if I want to do lines as opposed to markers, I can do solid, dotted, dash dot, completely dash, or no line. So these are all arguments. There is a syntax where I use all three of these, where I have both markers and lines, or colors, markers, and lines. And also there's an option where you can have the color and the line. And the reason it's distinguished from the markers are that all of the line characters are different than any of the marker characters. So you can have either 1, 2, or 3, and the context is can be determined. And then this help information gives additional ways of using it, but our use of it will be pretty basic and straightforward. Then the last thing I want to mention is that after I do the plot command, what I'm going to do here is execute the command show at the front. And what this does is, in this area right here, if I plot it, the first time I plot it, it automatically puts the window in the front of the MATLAB screen. But then later on, if I go back and start doing something in MATLAB, it gets hidden by all of this. So if I want to again see it, one option would be to go and actually click on the icon of the figure and have it display at the front. But another way you can do it within the script itself is just indicating this command SHD, I mean show figure at the front. So after plotting it, it'll make it a window that appears in front of anything else within MATLAB. And then after I do the plotting, what I'm going to do here is execute a command called hold on. And what hold on does is it sort of fixes the plot that I've just done, so that if I issue a second plot command, it puts it on that same plot. If I didn't have the hold on, the next time I executed a plot command, which I'm doing here in the next cell, it would erase the previous plot and then do this plot. So without the hold command sort of freezing everything to allow multiple plot commands to execute on the same axes, it would constantly create a series of new plots. And then when you're finished putting new plots onto the same axes, you can execute hold off. And what hold off does is then allow you to, the next time you do plot, to start with a new figure and a new plot. So that's sort of part of the syntax that is used in MATLAB to do plotting. Again, very similar to Python plotting. It's all very similar way of doing things. So I'm going to go ahead and execute all of this. And here I'm doing axes equals equal, as opposed to having X and Y have different scales, because I want it to be the same X and Y scale. So I'm going to execute all of this, F9. And you can see here it's plotted. Notice these are the black square markers corresponding to the 3 points. This point right here is the 1, 1 point. Notice that it starts at 1 as opposed to 0. It basically tries to fit the axes as close as possible around all the points. Here's the 7, 1, and here's the 4, 5 point. And then this next cell is going to plot again. And notice here, when I click back to the editor, the plot disappeared. That's why I want to execute this show at the front command again. And when I do that, and I'm going to then turn hold off, what I'm going to do here is execute the position of X, which corresponds to the optimal point that I just determined using the fminsearch. So now I have this new blue point, and the shape of the blue point is this asterisk, which shows as a star. Notice it disappeared again. So if I highlight it, F9, it'll bring it to the front. Another option, if you want to more easily be able to get access to your figure, is that if you look over here in the corner, it says dock figure. So if I do that, it adds it to the command window as a separate pane. So I can now switch between the command window and the figure. So this is another option. In my case, I typically don't use this, and the reason is that when I'm using MATLAB, I usually have more than one monitor. So I basically have the monitor, a second monitor used to display figures as I'm using MATLAB. So it's usually not an issue in practice. It's only in this case, by doing a recording, I need to keep everything within this one space for it to actually work. And then what I can do is I can actually use MATLAB to determine if the solution, and if you remember from class discussion, for the case of no weights on the problem, if I have 3 points and want to determine what is the optimal point, then it corresponds to the Fermat problem. And the optimal solution should be a solution such that all of the angles are 120 degrees. Essentially, it's a minimum energy solution. I can check that by using a trigonometric function within MATLAB called arctan2. And what that does is allows me to calculate the angle in radians. So I'm going to go ahead and execute that. And here I have the 3 angles. And here I can't tell if they're actually equal to 120. So I'm going to use the difference command. And it looks at the difference between the first and second and the second and third. I'm going to ignore the difference between the first and the third, because if the first 2 add up to 120, then it should be fine. Notice here it's not exactly 120, and the reason is this is a numerical procedure, so it's not going to give you exact answers typically. So for our purposes, I would say both of these are exactly equal to 120 with respect to numerical accuracy. So that does verify that that is exactly the solution that we did find for this problem. The next problem that I'd like to look at is to take those same 3 sets of points and add to it weights to turn it into a 2-dimensional mini-sum weighted distance location problem. So I'm going to go ahead and redefine P just in case, for in this case it's still there and it hasn't changed. But I'm going to, just for good practice, I'm going to go ahead and redefine all of that. And I'm also then going to define the 3-element weight vector. And a lot of applications, the weight vector might correspond to the number of trips that you're actually traveling that distance. That corresponds to the first homework problem where we looked at weights as the number of trips traveled. And what I want to do then, and this would then again correspond to what was done for the solution to the homework problem, is take the product of the weight times each corresponding distance. And if I do it in this case, what I end up getting is a 3x3 matrix. And really what I wanted to get is just a 3-column vector where I take the distances, which are already a column, and then just multiply them times the weight. And the reason that this didn't work is in terms of MATLAB compatibility, it basically took the W matrix, which was a 1x3, and expanded it to be compatible with the distance column vector, and I ended up with a 3x3 matrix, which is not what I want. So to force it to do what I want, I can do like I did with the X in the previous class. I can use the parentheses with a colon to force it into a column vector, and then I can take the product of it. So I'm just going to highlight this and execute it, and now I get what I want, which is the weights times the distance. And here I'm going to define a function handle that gives me my objective function. In this case, I want the minimum sum, so I want to do a summation of all those weights times distances. So I'm going to use that to define my function handle. And I can then use that function handle. X0 is the mean value defined previously. And I get the point 3.07 and 2.38, which is different than the unweighted example. And the total cost in this case is 36.055, which is a total weighted cost of distance times weight. If I want to check and see if the majority theorem actually works, we said in practice that, yeah, it should work if any one existing point or facility has more than half of the total weight, then the optimal solution is always going to be that point. And to be able to test that, what I'm going to do is first take the sum of all of the weights, which is 12, then take half of that, 6, and then add 1 to it. So I'm going to use that, and then I'm going to assign that to the weight to the third point. So now the third point with a value of 7 has more than half of the total weight. And when in this case, now I have to redefine my total cost that I did up here. And the reason is that I've changed my weights, and the weights are not one of the variable points. They're the fixed points along with the p-values. So in order for that to work, I need to redefine the function handle. That's one reason why instead of using a function handle, doing this as a function, a .m function can be handy, is that as a function, you don't have to go back and keep redefining it. As an alternative, you would supply 3 input arguments, x, and then the w and the p. And every time you call the function handle, they can all have different values. So I'm going to then evaluate this, redefine that, which essentially redefines my function handle, and then solve this. And I get the points 4, 5, and 40. And that point corresponds to, again, within the realm of numerical accuracy, that corresponds to the 4, 5 point. The 4.99 is close to 5. All right, this next example corresponds to the one-dimensional location problem with procurement and distribution cost that was discussed in class. And what I'd like to do here is show you how, instead of just doing it by hand and on the logistics network, that works fine for very simple problems, but once you know what the basic mechanics are, it's useful to be able to translate that solution into something that can be solved within a MATLAB script. And in that case, you can then handle more complicated problems. So first, I'm going to determine the monetary weights. I'm going to go ahead and just execute this. And here I'm making the distinction between the inbound versus the outbound side. And I'm going to define F, R, and W separately for inbound and outbound. And then for inbound, in order to get the inbound, I need to take the results in terms of F, the sum of the F values for the outbound side, which is my total demand. So here I'm summing up my total demand, which is 60, and then I'm going to apply the bill of material ratio, which is 2 and 0.5. So once I've defined a bill of material ratio, then I can determine what is the required input in terms of tons for the two suppliers. So I get values of 120 and 30. And then here I can apply the transportation rate of 0.33. And then get the monetary weights for the inbound side here. And then finally, I'm going to compose both of these together into one W vector, putting the inbound side first, followed by the outbound side, and the units here that are in dollars per mile. And then next I can determine the locations, and here P is going to be a one-dimensional set of locations corresponding to the 5 different cities where we have suppliers and customers. And what I'm going to do here is define P first as a row vector, then take the transpose so that it turns into a column vector. So those are the mile marker coordinates. And again, unlike solving this problem by hand, which we can do because it's a one-dimensional problem, because we're doing it on a computer, we do need to have the coordinates. And then like before, I can then define my function handle. It's going to be, again, the same Euclidean distance function handle. In this case, since it's along one dimension, I could also just do the absolute value of the difference. I don't need to actually do the complete Euclidean distance, but this allows me to use the same handle both for one and two-dimensional Euclidean distance problems. And then, like before, define my function handle, call fminsearch, using as my starting point the mean value amongst all of the 5 city coordinates. And here I get a optimal value of 190, and 190 actually corresponds to, I believe, Winston-Salem, the mile marker for Winston-Salem of 190, which is the same that we found by solving this problem by hand. And then the last thing we can do is to look at, for this problem, whether or not this problem is a weight gaining or weight losing. In terms of physical weight, we can take the sum of the tons in versus tons out, calculate each of those. In this case, we have more physical weight going in than going out of the facility. So it's physically a weight losing facility. But if we look at it from a monetary weight point of view, in this case dollars per mile, then we have 49.5, which is less than 60. So in this case, it's a weight gaining facility without the qualification of monetary weight, because within logistics and location theory, it's usually understood that the reference to weight gaining is monetary weight gaining and not physical weight gaining. Again, that's one of those things that can trip you up if you're not aware of that. Next thing I'd like to look at are 2 other types of two-dimensional location problems that are not mini-sum problems. And the first is the Minimax problem. So for the Minimax problem, I'm going to use the same 3 p-points. So I've defined those and the same type of Euclidean distance function handle that we used before. And then the only change here now is when I get to the point of actually defining the objective function handle. Instead of taking the sum of these distances, I'm going to take the maximum of these distances, define that function handle. I can then apply fminsearch using the mean value as the starting point, and then end up with this solution. And if I want to look at what are the distances from that solution to the other 3 points, I end up with a case where all 3 are exactly the same, which for the Minimax problem is what you would expect, because if I could move the point and reduce the distance in one direction, it would correspond to an increase of the distance in the other direction. So the only point that doesn't have that characteristic is the point such that all the distances are the same. So at that point, there's nothing to gain by moving. So at that point, it's the optimal location. So that's an easy, straightforward problem. Again, it's like the mini-sum location problem in that it doesn't really matter where we start. We end up with a solution to the problem. The next problem is the sort of the reverse of the Minimax problem. Here, we want to maximize the minimum distance. So within MATLAB optimization routines for nonlinear optimization, there's no function that automatically, instead of called fminsearch, is fmaxsearch. So we can't directly determine the maximum of a function. So as a way of getting around that limitation, we can basically try to take the minus sign of the value and then minimize that, which corresponds to maximizing. So if we take the minimum of a function, we kind of essentially flip it upside down so that our minimization procedure is actually maximizing the function. So all I'm doing here in this case is applying a minus sign to the minimization, which is all we can actually be solving. So now I have a function handle that takes the minus of the minimum of all of the distances. And then if I use a mean starting point for fminsearch, run fminsearch, I end up with this solution. Again, looks like that might be a good solution. But instead of taking the mean value, what if I, again, unlike the mini-sum problem and the Minimax problem, which doesn't really matter where I start, here, if I pick a different starting point, in this case, it's going to be the 0, 0 point. If I pick that different starting point, now what happens is I got essentially really is an error message from fminsearch saying that the number of function evaluations has been exceeded. And this is the current function value. You can see it's a very large negative number. And if you look at the coordinates and the value, it's something, minus number raised to the 41 power. So it's a really large negative value solution. So it's essentially going off to infinity. And the only reason it's stopping is it's reaching some limits within the optimization routine. But it's essentially gone off to infinity. So we don't have a solution. As we discussed in class, the reason for that is that we are looking at an unbounded solution. If you think of solving like a obnoxious facility location, if you don't put bounds on where it's feasible to actually locate, the best solution is always out in the middle of the Atlantic Ocean somewhere, as far from, any inhabited region of the country. So you always have to have some type of bound. So our next problem then is, how do we actually go about implementing the feasible region that was discussed in class? And first, before we do that, it's, I think, helpful to be able to plot what is the surface of the function. Previously we plotted just the 3 points and the optimal point, but we didn't look at what is the actual surface corresponding to the problem. One of the reasons is that for convex problems like we were solving, it's just essentially a big bowl that has a single optimal. But in this case, we have a problem that actually has different optimal solutions. So it doesn't have a single optimal solution. So it's a non-convex optimization problem, our first example of that type of problem. So to do that, to be able to plot a two-dimensional surface, we can use the function that's part of MATLAB called mesh grid. And what mesh grid does is, for a range of values for x and y coordinates, in this case for the x coordinate, I'm going to start at -4, which is outside and to the left and below of the set of 3 points, and then go in increments of 0.2 all the way up to a maximum value of 12. And then for the y coordinate, again, I'm going to start at -4, and in this case go all the way up to a value of 10. And then what mesh grid does is gives you all combinations of x and y values, and since these are both defined as vectors, it essentially takes the product of both of those and then returns two matrices, and the size of the matrices would be the number of rows corresponds to the number of values of x, and then the number, of y, and then the number of columns corresponds to the number of values of the x. So when we execute this, I'm going to keep the semicolon here because these will probably be large matrices. Go ahead and execute it. If I look over here into my workspace, I can see that the x that was created actually has dimensions of 71 times 81, and the y has the same dimensions of 71 times 81. So I have the product of 71 times 81 different values that I have x and y coordinates for. And then what I want to do next is determine what is the function value at all those x, y points given to me by mesh grid. And I first can define the z matrix, which is going to be the function value, as being a matrix of zeros the same size as x. And then here what I'm doing is a series of 2 for loops, and I'm essentially looping through the x matrix, first over all of the first dimension, and then secondly through all of the second dimension. The first dimension are the rows of x, the second dimension are the columns of x, and then for each of those, in this case each of these i's and j's, I'm going to explicitly look at, for this value of x given by xij, and this value of y given by yij, apply that single two-dimensional point to the function handle and assign it then to the corresponding z matrix value. So I'm going to loop through and do all of that. So I've calculated z. If I go over here to the workspace, look down, I can see that my z now has the same dimensions as this. And then here what I'm going to do is I'm going to open up a new plotting figure, and in MATLAB the command figure, when I execute it, you can see it just pops up a second figure. The reason it's a second figure is that I previously plotted the other one, so it keeps track of the total number of figures that I've created, and it's shown over here as 1. If I had deleted that 1 first, then that would show up as is. And you can see here I've actually lost that. So if I want to bring it to the front again, I can F9 and it'll display. That's actually figure 1. That's what I don't want. What I do want is figure 2, which is over here. So what I'm going to do here is I'm going to first delete figure 1 since we don't want that anymore. And then for figure 2, I'm going to go ahead and dock it so that it's accessible so we can get to it. So in this case, it's just a blank slate. Nothing's been plotted yet. And then the last thing is I'm going to execute a command called surface contour plot. Again, this is not something you'll be using yourself or don't need to use, but it's useful for illustrating purposes. And I'm going to again give it 3 arguments, the x, the y, and the z matrices. And then if I had not docked it, then the shg command would bring it to the front. And then I'm going to put the hold command on. So if I want to do subsequent plotting, I can do it to the same figure. So I'm going to F9, and now it's brought it to the front. And here you can look and see that this is the shape of the function. This contour plot, in addition to the surface, it also shows the two-dimensional contour line plots here at the bottom. So you can see that there are essentially three optimal points, and I shouldn't say optimal points, but there's 3 extreme points. And really what we're trying to do for this problem is, in some sense, these 3 points are the 3 worst points. because they're close to the existing points, so we have very small distances, and we're trying to maximize the minimum distance. So really we're trying to get as far away from these 3 points as possible, and to make it feasible we have to do it within the context of some feasible region. And, think of the Wake County boundary as a feasible region, or the rectangle that we talked about in class. So that's the problem we're looking at. The last thing is we might want to also be able to look at more characteristics of the problem. So what I'm going to do here is, if I look over here, and if this was not docked and standalone, it would be on the toolbar of the figure window. But since I've docked it, it's turned over here. And what I'm going to do is I'm going to click on this command right here, which allows me to rotate the figure. So now when I go back to the figure, you can see here I can move it around and see. So this is one of the really nice features in MATLAB. It has very nice graphic capabilities that allow you to see the characteristics of the problem. And it's amazing the amount of times in research when you have sets of data and problems where you don't really have any type of theoretical insight into what exactly it should be doing or what are the characteristics of something, that plotting like this is very helpful to get a handle on what is actually the characteristics of what you're looking at. So this is a very nice capability. Again, I think for this problem it's probably a little bit of overkill, but this whole set of how you actually use the mesh grid together with the calculation of the function value and then the surface contour plot is a very general technique that you can use for a lot of different types of applications. So the next thing I want to do here is to determine the feasible region. And to make it a little bit more general, as opposed to, since I know those 3 points P, I could just go ahead and put values in for the feasible region. But in this case, I'd like to show you an example of being able to do it in a little bit more general manner. And to do that, I'm going to define R, and I'm just going to first go ahead and execute it. First, I'm going to click back to the command window and hit F9. And what I have returned is a 2x2 matrix. It's the same values that were shown in class. The first point is the 0, 0 point, and the second point is the 8, 6 point. The way I've calculated it, and I think a good default way of calculating a region like that for a set of points, is to define the region by the lower left and upper right points. Those 2 corner points are enough to define the region. One advantage of doing it that way is then if you take the difference column-wise, you get the span of x and y. So if I do the 8 minus 0, 6 minus 0, I get the total length in x and y direction of the region. And in this case it happens to be 0, but that lower left point could be any value. And then taking the difference allows you to get the x and y extent. And you'll see in a few minutes why that's useful and handy in practice. Let me just talk a minute about how I did the region calculation. What I did is I defined for my lower left point the lower left, the left column of the region. The way I've determined that is by using the minimum command. And the minimum command, the syntax of it, I had to use 3 input arguments. The reason is that the minimum command, one way of using it is, if you have just a single array or vector, it gives you the minimum value of that vector. That works great for vectors, but for matrices, it's indeterminate which one. So by default, it does it across the first dimension. So in this case, I'm forcing it to do it as a minimum across the first dimension. But notice that the 1 indicating the dimension, unlike the sum command, it's not the second input argument. In this case, it's actually the third. And the reason is that the minimum and the maximum commands have one way of using it such that if you have 2 arrays, you can supply those as the first 2 arguments with no third argument. And what it does is then element by element, it returns the minimum value, and in this case, maximum value. So since we don't want to use that syntax, I'm just putting square brackets in the second argument. And essentially what that is telling MATLAB is to ignore that second argument and instead look at the third argument, which is telling MATLAB for this minimization problem, minimize across the first dimension. And then I'm taking all of those minimum values and then subtracting 1. So the first time I call it, I get 1, 1. Then I can subtract 1 from that. I get 0, 0. Likewise for here, I'm taking the maximum and adding 1. I get the 8 and the 6, and then I can put them both together, and I get my R value. Okay, the next thing I'm doing is to be able to work within that feasible region. I'd like to be able, for a particular point X, to be able to determine is it within the region or not. So I'm defining a function handle that does that calculation. And the way it works is it starts with the, then the X itself is actually a XY point of 2 dimensions. There's an X and a Y value, and it's a row vector. So X1 is the X value, and then X2 is the Y value. So for the X values, first I'm going to look at, is it greater than or equal to the bottom left point, which is R11, and this is logical, and is the point less than or equal to the top left point. In that case, it's within the X value within that region, and then I can do the same. And then another thing that has to be true is for the Y point, is it greater than or equal to this corner, and is it less than or equal to the upper right corner of the region. So if all of that is true, then it returns logical true. If not, it returns logical false. So I've defined this function handle. I can now test it with a few points. So if I put 1, 1, is 1, 1 within the region? It returns true. If I put 10, 10, 10, 10 should be outside the region, since the region is only 8, 6. Here I get a logical 0 returned. To be able to then use it within an optimization, I have the logical test for a point, whether or not it's within a region, and then to be able to use it within an optimization problem, I would like to be able to, if a point is not within the feasible region, to have it return a value of infinity. So if a problem is trying to minimize something and it gets a value returned of infinity, it's never going to select that as an optimal value. It'll try to get as far away as possible from infinity. So to be able to do that within a function handle, I can't use a traditional type of if statement, because the function handle has to have a single command. So as an alternative, I can use the IFF function that I've defined, and it's basically just a simple if statement. If A is true, do B, otherwise return C. So that's all it's actually executing. And if here I want to test how it works for those 2 previous points, here if it's within the region, return yes, otherwise return no. For the first point I get a yes, and for the second point I get a no. So that is working, and I can now use it for my Maximin problem. So I'm going to take both the IFF function and the is in rectangle together with the negative handle here. And so if it was within the region, I return my function handle value. If the point's outside of the region, then I return infinity. So I've defined the function handle. So now I can, for the point 1, 1, when I solve that, I get 0. 2, 2, I get minus 0.14. Here I get infinity because minus 4 is outside of the feasible region. So it seems to be working as expected. Next, what I'm going to be doing is picking different sets of starting points, because again, this is a non-convex problem. We saw that it has 3 different extreme points corresponding to the worst possible solutions, locating right at a point. We want to get as far away from that as possible. It's a non-convex situation. So where we start is going to impact what we end up with in terms of solution. If the first case is to pick the mean value, like we did previously for the convex problems, as our starting point, and then run fminsearch. If we do that, we end up with a value here. Here the important thing is to look at the value 3.12, and it's a negative, so we actually want as large negative value returned as possible, which would be, in our case, the largest maximum return. If we pick 0, 0 as our starting point, F9 that, I get a smaller value. Here I'm going to pick as my starting point the first point, P1. If I pick P1 as my starting point, I get the same 3.12. If I pick the second point in P as a starting point, I get a better value, 4. Again, I'm taking the negative of what's returned, so this is a positive 4. And if I pick the third point, I get even better, 4.1228. Question then, is that the best point? Is that the best I can do? I've essentially looked at the average p-value starting point, the 0 point, and then all 3 points. So I've gotten these 5 different values, and I think at least 2 or 3 of them are different. The best one so far is this last one, but then is that really the best one? So what we can do is to be able to look at a larger set of points, we can pick random starting points. So what I'm going to first do is set the seed of this random number. That way, if you want to duplicate this, you'll get the same results if you execute in the same sequence. Otherwise, depending on if you've called random or not, different times you may get different random starting points for your random number stream, so you get different solutions. And what could happen is you run it and you look and you got a really good value, but if you didn't set the seed, you'd have no way of duplicating it. And unless you've managed to record that value, you might not be able to easily duplicate it. It'd be terrible to go back and say, I found this really good value, but I can't duplicate that value because I don't know what the random number generator was that I was using and what starting point. So the issue of kind of keeping track of and being able to retrace your tracks is really important to be able to document your work. So in this case, one way of doing that is setting the seed, and then if I execute a fixed number of times, I should get the same fixed set of sequences. So I'm setting the seed, F9, and then here what I'm going to do is, and this I mentioned earlier about being able to use differences on that region. What I can do in terms of defining a random starting point is I want the random starting point first to be inside of the region. So I'm going to take first row, the 0 point, which is the bottom left point of the region, and then I want to add a offset from that. The extent of the x and y is determined by the difference, 8 and 6. So the x coordinate has a span of 8, y a span of 6. And in this case, 0, 0 doesn't really illustrate it well, but I could, this would work for any bottom left point, starting point for the region. And then to that, I want to multiply that times a random number that's between 0 and 1. And what that does is then multiply 8 times 0.19, and in this case 6 times 0.62. So this extent 8 and 6 is going to be multiplied by some value between 0 and 1, and that'll give me my random points within that square region. So in this case, since I've already called random once, I'm calling it a second time. So you'd have to, if you're trying to duplicate exactly my numbers, it's going to be slightly different. So if I want to be able to make it a little bit easier, let me go back and reset the seed. And now if I go ahead and execute this point, I get that as my starting point. And now if I run the fminsearch, F9, I get minus 41210. If I look back up here, that's not actually as good as I found starting at point number 3. So that's not the best I can do. So here I can I'm going to evaluate the current selection. That'll do both the generation of the random starting point and the optimization. Here I've gotten 1, 2, 3, 1. That's actually even better than I found starting at point 3. So far that's actually my best point, and that was found in the second or third time running it. Again, I can't duplicate this if I never find that good value again. Here I'm just going to hit Control Enter, which will execute everything in this cell. That's not as good. That's as good. Notice that the same as good numerically is the same 6. Here it's exactly 6. Here it's 5.999. Again, that's because of numerical precision is not exact. You'll see slight differences. I'm going to Control Enter again. Here I get the same value of, instead of 0, I get 8 as the x value. And basically it's symmetric along the x dimension, it looks like. So I'm essentially getting optimal points along the boundary of that region. Run it again. Here I get another different answer. Looking at these, it looks like I've gotten about 7 or 8 or 9 different answers, or maybe even 10 or 12 different answers. So this is an example of a problem that has lots of different answers. In terms of practice, how would you actually solve this problem? Well, this is an example of most problems in logistics engineering that are not simple and easy problems, and you don't really have any guarantee of any expectation of this is the optimal. So the best that we can hope for is this is the best known solution. So unless you can show that you've tried everything exhaustively, the best we can say is that for this set of points, this is the best solution that we've been able to find.